Hello everyone. So this is the fifth hour of electrostatics and gravitation. But now we are not talking in common terms. Today we are going to talk about electro-specific topics. So in this hour and the next hour we will talk about only the things which are understood in electro but not in gravitation. So which are the things which are there in electro but not in gravitation? There is Gauss law, there is dipole, and then there is property of conductors. In this hour, we are going to focus on Gauss law and dipole. Beta, here dipole is really important. Question come every year from dipole. So put your attention properly when I teach you dipole. Moreover, even in dipole, the most important part is dipole in a uniform field. That particular concept will be used here in electro as well as will be used in magnetism. So that particular concept, the property of dipole in a uniform field, that particular part is important. So first, in this hour, we are going to talk about Gauss law. Now, before we talk about Gauss law, we need to understand something called flux. So, what exactly is electric flux? Electric flux represents the number of field lines crossing a given surface area. If you consider any given surface area in the space, and if no number of field lines are crossing it, you will say that the flux linked with this surface is high. If less number of field lines are crossing the same surface, then you will say that the flux linked with this surface is low. So what exactly is electric flux? Flux represents the number of field lines crossing the surface. Here I will like you to pay special attention to one of the word, which is crossing the surface. Crossing the surface. This crossing word is important. How will elaborate in little while, but remember that crossing the surface matters. So now, what is the definition of flux? If you say that work is the concept using which we can explain transfer of energy by the application of force, that doesn't make any sense. Mathematics is the language of physics. So every time we have got some physical quantity, we have to associate mathematics with it. So what is the basic definition of flux? So we say that if we have a small surface area, ds means infinitely small surface area, and at the place of this infinitely small surface area, if the electric field intensity is E, then the infinitely small flux linked with this particular infinitely small surface area is given by d phi. Phi is the symbol for flux, equals to E dot ds. Here you need to understand multiple things. First, you get flux from the dot product of electric field and area vector. Since you are getting flux from dot product of electric field and area vector, flux is a scalar quantity. Flux is a scalar quantity. Second thing, bacho, here we have taken area as a vector. When I say area vector, what does the area vector mean? Sir, a vector is a quantity which has got both magnitude and direction. Yes. So when I say area vector is ds, it means that the magnitude of the area is the infinitely small area ds, and the direction is taken normal to the area. The direction is taken perpendicular to the area. So when I say an infinitely small area vector, think of the magnitude of area as the area, and think of the direction as the direction perpendicular to the surface as the direction normal to the surface. So the area vector is taken in direction normal to the area. This is something you need to know. Now, in the world of physics, we define everything in infinitely small format. We say that the infinitely small flux linked with an infinitely small area ds is given by d phi equals to E dot ds. But what if we have a big surface? Then for the big surface, think of every infinitely small area, and for each infinitely small area, look at the electric field vector. Take its dot product with its infinitely small area vector and keep on adding all the terms infinite number of time to cover the entire surface. And adding up infinitely small quantity infinite number of time is integration. So we say that from here, integrating both the side, the net flux linked with a surface is nothing but integral E dot ds, integrating both the side. If the electric field is constant, only then you can pull E out of the integration. So for uniform electric field means constant electric field. You can write the flux link to be equals to E dot S. It's high probability that the question that will come in your NEET examination, there the electric field strength will be constant. So what is flux? Flux represents the number of field lines crossing the surface. What is E? The electric field intensity. What is S? The surface area. Now S is actually the surface area vector. You have to consider both magnitude as well as direction, and the direction has to be taken normal to the area. To understand flux better, let's take up an example. So the question goes like, find the flux linked with the three surfaces due to the electric field equals to 2i cap plus 3j cap plus 4k cap as shown. So there is an electric field 2i cap plus 3j cap plus 4k cap existing in space. This means that the electric field strength in the x direction is 2, electric field strength in the y direction is 3, and the electric field strength in the positive z direction is 4. You need to determine the flux linked with these three surface areas. Which three surface areas? A square of side length A placed in the xy plane, a circle of radius r placed in the yz plane, and an ellipse placed in the xz plane. So you have got a square in the xy plane, a circle in the yz plane, and an ellipse in the xz plane. So what will be the flux linked with these three? It's very easy. For uniform electric field, which is given here, you can simply write flux as E dot S. Now how will you write the area vector for this square? So sir, the magnitude has to be same as the area. For a square, the area will be A square. And the direction has to be taken normal to the area, perpendicular to the area. So which direction is perpendicular to the plane of this area? So this area lies in the xy plane. So the direction perpendicular to it is the z direction. So you will say that the magnitude of area is A square and the direction is z direction. So you will simply say A square k cap. So for square, the area vector will be A square k cap. So the flux, which is E dot A, will be given by 2i cap plus 3j cap plus 4k cap dot the area vector, which is A square k cap. Taking dot product is one of the easiest mathematical operation to do. Simply multiply the coefficient of I cap with, okay, there is no I cap, so 0. Coefficient of j cap with coefficient of j cap, okay, there is no j cap, so 0. Coefficient of k cap with coefficient of k cap, so you simply get 4a square. So the flux linked with this square is nothing but 4a square. Somebody might say, sir, you could have even taken the area vector in the negative z direction and you could have written here minus a square k. You can do that as well. So you will get the flux linked to be minus 4a square. It is equally good answer, but I personally like to stay away from negativity in life. That's why I take the direction which gives the answer as positive. But here reporting the answer as minus 4a square is equally valid. Now, how do we write the flux linked with this circle? So for the circle, you will write the area vector to be the magnitude of area pi r square, and the direction has to be perpendicular to it. This lies in the xz plane. So the direction perpendicular to it will be the x direction. Since the circle lies in the yz plane and the direction perpendicular to it is x direction, so the area vector will be pi r square I cap. So we can say for circle, the area vector will be pi r square I cap, and the flux link will be simply E dot A. So that will be 2i plus 3j plus 4k dot pi r square. Simply multiply coefficient of I with I, j with j, k with k. So you get 2 into pi r square. That's the flux linked with the circle placed in the yz plane. What will be the flux linked with the ellipse placed in xz plane? For the ellipse placed in xz plane, the area vector has to be taken normal to the surface. That will be along the positive y direction. And we know that for an ellipse, the area is given by pi into length of the semi-major axis, which is A, into length of the semi-minor axis, which is B. So you will say for ellipse, the area vector will be pi AB j cap, pi AB j cap. So the flux linked has to be 2i cap plus 3j cap plus 4k cap dot pi AB j cap. So when you take it, you simply multiply coefficient of j cap with j cap, so you get 3 pi AB. Sir, what are you trying to explain to us with this particular example? Two things. First, the direction of area vector has to be taken in the direction normal to the area. Second thing beta, the flux is because of the field line crossing the surface. Now think of only this square plate. Here we have got electric field in three directions. We have got electric field along the x direction, which is 2. We have got electric field along the y direction, which is 3. And we have got electric field in the z direction, which is 4. Now tell me, out of these three fields, the 2 lies in the plane of the square. The 3 in y direction lies in the plane of the square. The field line which are crossing is the 4 lying in the z direction. Since the electric field line of 4 crosses, we get flux linked with this square because of the field strength of 4. And that's why the flux came out to be 4 into a square. Similarly, the field lines which are crossing this circle placed in the YZ plane is of strength 2 along the x direction. That's why we got 2 times its area pi r square. And similarly, the field lines which are crossing this ellipse are the one in the y direction. The x1 is not crossing, the z1 is not crossing, the y1 is crossing, and in the y direction the field strength is 3. That's why we got the flux linked as 3 pi AB. So remember this thing, the flux is due to the field line that crosses. The flux is due to the field line that crosses. Okay, let's take one more example to understand it. Question goes like, determine the flux linked with the square plate. The field is in the plane of the plate. So there is a square plate of side length A. We have got electric field E in the same plane making an angle theta with the side of the square. What is the flux link with this particular plane? So without even thinking, student starts doing that. Okay, flux equals to E dot A electric field dot the area vector. So that will be E into S into cos theta. So that will be E into A square into cos theta. So that will be the answer. No. Here understand that the electric field, though it makes some angle with the side length of the square, the electric field lies in the plane of the square. It is not crossing it. Since the electric field lines are not crossing the area, the flux linked with these particular electric fields will be 0. So as the area vector of the square plate is perpendicular to field, think that the area of this square is on the screen of your device. What will be the direction of area vector, sir? We can take towards us or away from us, right? So if you take the direction towards you, the area vector and the field are perpendicular. Since the area vector will be normal to the surface and the field lies in the plane of the surface, the angle between them will be 90. So as the area vector of the square plate is perpendicular to the field, the flux linked with the plate is 0. Why? Because no electric field lines are crossing it. That's why the flux linked with this particular square plate has to be 0. So here I am trying to emphasize on the definition of flux. Flux represents the number of field lines crossing the area. If the field lines are not at all crossing the area, then the flux linked with them is 0. So now we will talk about the most awesome formula in physics I have seen, that is the Gauss law. Gauss law is such a beautiful formula and its interpretation that you will also fall in love with it, but you will have to understand first from where it came. So assume that we have a charge q placed at the center of a sphere and the sphere has a radius r. If I ask you what is the electric field due to this charge q at a point on the surface of this sphere, you will say, sir, the electric field strength has to be kq upon r square. Now if you think of an infinitely small surface area here, dA, the infinitely small surface area will have its direction in the same direction as the electric field. So if you take the dot product of electric field and the infinitely small surface area, the angle between them is 0 and cos 0 is 1. So if you write d phi to be equals to the electric field strength dot dA, and then you take the dot product as E into dA into cos of the angle between them, and cos 0 becomes 1, so you simply get E into dA. So you will say here, the infinitely small flux linked with this infinitely small surface area dA will be given by d phi equals to the electric field strength here, kq upon r square into the infinitely small area dA. Now once we have got what is the flux linked with this infinitely small surface area dA, how to write the flux linked with the entire sphere? So you will have to integrate, yes, but the integration here is simple. Integrating both the sides, you will get the flux equals to kq upon r square into the whole surface area of the sphere. The whole surface area of this sphere will be equals to 4 pi r square. So what you get is kq upon r square into the whole surface area, which is nothing but integral of the magnitude of area of an infinitely small area dA, and you get the whole surface of sphere, that will be 4 pi r square. Now here bachcho r square get cancelled. So what you get is flux equals to k into q into 4 pi. In place of k, you can write 1 by 4 pi epsilon naught. So you get 1 by 4 pi epsilon naught into q into 4 pi, and you can cancel out the 4 pi with 4 pi, and you will get flux equals to q by epsilon naught. Now what does the flux represent? So flux represents the number of field lines coming out from this spherical surface. Yeah, I am saying spherical, do not think circular, think three-dimensional spherical surface. So the net flux coming out of this spherical surface, which represents the number of field lines crossing this whole spherical surface, equals to the charge inside upon the epsilon naught. Okay. Now, what does Gauss law says? Gauss law says that the net flux coming out of a Gaussian surface. What is a Gaussian surface? A three-dimensional closed imaginary surface. A three-dimensional closed imaginary surface is a Gaussian surface. So, if you have got any charge q, you can think this charge q to be encapsulated inside any random surface. Think 3D. Now, this whole surface can be treated as a Gaussian surface. So, the Gauss law says that the net flux coming out of any Gaussian surface, a three-dimensional closed surface, is nothing but the net charge inside the surface upon epsilon naught. And we can write this net flux coming out to be equal to integral of E dot ds. Now you might be thinking, what is this sign here? Means on integration, what is the circle? This circle represents the closed integral. It means that when you think of the three-dimensional surface, think of every small area. Look at the net electric field at any point on every small area. Take the dot product of the electric field there with the area vector there, and keep doing this for the entire three-dimensional Gaussian surface. And when you add it up for the whole closed Gaussian surface, the closed integral of E dot ds gives you the net flux coming out. And this net flux coming out, which can also be written as closed integral of E dot ds, is nothing but the total charge inside upon epsilon naught. Now here you should know few important things about the Gauss law. The Gauss law says that the net flux coming out of a closed surface is equal to the total charge inside upon epsilon naught. Now here, this is kind of an outrageous statement. Why? I will explain each part. Do not perplex, but keep listening carefully. So the flux coming out of a closed surface is independent of. So the rule simply says that the net flux coming out of a closed surface equals to total charge inside the closed surface upon epsilon naught. The net flux coming out of a closed surface is independent of, first, position of charge inside the closed surface. So if you have got a closed surface, and let's say I have got a charge q1 here, and I ask you what is the net flux coming out of this closed surface, you will say q1 by epsilon naught. Does it depend upon where I have placed the charge inside this closed surface? No. So the net flux coming out of a closed surface is independent of the position of charge inside the closed surface. You have placed it here or here or here or here or here or here. Till the time the charge is inside the surface, it doesn't matter where you have placed it inside the surface. Second, the net flux coming out of a closed surface is independent of shape of the closed surface. So if you have a charge q and you think of one Gaussian surface enclosing this charge, it can be in the shape of a cube. It's just that the charge should be inside the cube. Now it's not looking to be inside, let's say here. Or it can be a sphere. It is independent of the shape of the closed surface. So whether you put a charge inside a cube, the net flux coming out of that cube, cubical surface, will be q by epsilon naught, or you place it inside a sphere, the net flux coming out of the sphere will be q in by epsilon naught, which will be q by epsilon naught. And the third thing, it is independent of size of the closed surface. This is my favorite question. I ask to students, if you have a charge q here and you think of two Gaussian surfaces around it, one a small sphere, another a big sphere. Tell me, more flux will be linked with which Gaussian surface, the small sphere or the big sphere? So you will say, sir, the flux linked with a Gaussian surface equals to the charge inside upon epsilon naught. Now, the charge enclosed by this small surface is same as the charge enclosed by the big surface. Hence, the flux linked with both the Gaussian surfaces is going to be Q by epsilon naught. Hence, you can see it is independent of the size of the closed surface. So what does the flux linked with a Gaussian surface depend upon? Only on the charge inside the Gaussian surface Q in. Now here one more important thing. We can say that the net flux coming out of a Gaussian surface equals to the closed integral of E dot ds. Here the electric field E is due to inside charges, outside charges, all the charges. Better remember that this electric field E is the net electric field at a point on the surface. It is the net electric field. It is the electric field both due to inside charges as well as outside charges. Hence, electric field is the electric field due to both the inside and outside charges at a point on the surface. So if you have got, let's say, two charges Q1 and Q2 inside the surface and one more charge Q3 outside the surface, the net flux coming out of this Gaussian surface will be nothing but Q1 plus Q2 upon epsilon naught. But at any point on its surface, the field will be produced by Q1 and Q2 and Q3, all of them. So when we write here E, this is what? Electric field produced by the inside charges, outside charges, all the charges. You will say the electric field here is the electric field net. And the net electric field will be because of all the charges, both inside charges as well as outside charges. Sir, I've got multiple doubts. Like what? Why does the net flux coming out depend only on the inside charge? Why does the net flux coming out is independent of the shape of the closed surface? And why is there no effect of the outside charge even when while writing the electric field we are considering the outside charge? Very nice doubts. I will clear them all one by one. So now let's start understanding all these points. So the important points. Number one, flux can be understood as the quantity that represents the number of electric field line crossing. Think of field lines coming out of a positive charge in case 1 and in case 2. In case 1, we are looking at a surface area close to the charge. And in case 2, we are looking at a surface area away from the charge. I ask you simple question. More flux will be linked with which surface area? In case 1 or in case 2? You will say that, sir, it is visible that the number of field lines crossing in the case 2 is less. Since the number of field lines crossing in case 2 is less, the flux linked will be less. Or you can think using mathematics that the flux is nothing but integral E dot ds. Here the strength of electric field close to the charge will be more. So for the same area, since the strength of the electric field will be higher, the flux linked will be more. But what I want you to understand is that electric flux represents the number of field lines crossing. Since in the case 1, the number of field lines crossing are more, the flux linked is higher. Now, let's think of the second point. Let's say you have a charge Q, okay sir? And if you have a charge Q, electric field lines will come out in all directions from it. Here, I am bound to draw in 2D, but visualize in 3D, electric field lines coming out in all directions. Now think that you have got this first Gaussian surface enclosing it S1. There will be some number of field lines coming out of this particular Gaussian surface. How many? So all the field lines that are coming out of the charge are crossing this particular surface S1. You right? Now forget S1 and think of another Gaussian surface S2. Now tell me, in which case the number of field lines coming out of the Gaussian surface is more, in the case 1 or in the case 2? So all the field lines which are being created by this charge are still coming out of this Gaussian surface. Since all the field lines are still coming out, it means that the number of field lines coming out is same. Since the number of field lines coming out is same, the flux linked has to be same. So this tells us that with both the surfaces S1 and S2, the flux linked will be same as the number of field lines coming out is same, right? So we can say the number of electric field lines crossing both the surfaces is same. whether you take a sphere or some randomly shaped three-dimensional closed surface. Hence, the flux linked with both of them is same. Now, this particular example explains to us itself that it doesn't matter where is the charge placed inside the surface. It doesn't matter what is the shape of the surface. It doesn't matter what is the size of the surface. If the surface encloses the charge, all the field lines which will be created by the charge will cross the surface. Yes, and as all the field lines created by the charge will cross the surface, the flux linked has to be same independent of which type of surface you choose, right? So now let's move on and think why there is no effect due to a charge placed outside. So the net flux linked with a Gaussian surface is independent of the charge outside. Why? Think that you have a charge q which is placed outside a Gaussian surface. I am bound to draw in 2D but better visualize 3D. Now here you can see that at these points the field lines are entering into the Gaussian surface, and at these points the field lines are exiting the Gaussian surface. When the field line enters into a closed three-dimensional Gaussian surface, we say that the flux linked with those field lines is negative. And when the field lines exit three-dimensionally closed Gaussian surface, we say that the flux linked with them is positive. As the number of field lines entering is same as the number of field lines exiting, that's why you will say the flux entering is same as the flux exiting. When the flux enters, we take it as negative, and when the flux exit, we take it as positive. Hence, the net flux due to a charge placed outside is 0. So, the flux due to the field lines entering is taken as negative. The flux due to field line exiting is taken as positive. Hence, the net flux due to this outside charge is 0. And so we say the net flux coming out is nothing but the total charge inside upon epsilon naught. So that's why there is no effect on the flux linked with a Gaussian surface due to the outside charge. It depends only on the charge enclosed by the Gaussian surface. Why? Because if you have a charge outside, think of the field lines produced by it. The number of field lines entering will be same as the number of field line exiting. When the field lines enter, the flux is negative. When the field line exit a three-dimensionally closed Gaussian surface, the flux linked is positive. So the net flux is 0. That's why there is no effect of outside charge when we write the flux linked with a Gaussian surface, that is a three-dimensionally closed surface. So let's move on to understand some question. The first question goes like, there are 4 charges Q1, Q3, Q4, Q2. Question is, determine the flux linked with the Gaussian surface. So you will say, if this is a three-dimensionally closed surface, then the flux linked with it has to be equal to the net charge inside upon epsilon naught. The net charge inside is Q2 plus Q4. So you will say that the flux linked has to be nothing but the total charge inside Q2 plus Q4 upon epsilon naught. Question is, at a point on the Gaussian surface, when we find the net electric field, to that net electric field, do the charge outside contribute? Yes, Q1 and Q3 contribute. But to the flux linked with this Gaussian surface, do the outside charge contribute? Answer is no. Why? Because the number of field lines entering because of them is same as the number of field lines exiting because of them, and hence there is no flux linked with this Gaussian surface due to the outside charge. Keep this thing in mind. Let's see the next example. Example goes like, we have got this cylindrical Gaussian surface closed. Now the question says, for the charge placed symmetrically at the center of cylindrical Gaussian surface, a closed three-dimensional surface, if the flux linked with the curved surface is phi, if the flux linked with this curved surface of the cylinder is phi, find the flux linked with the flat surface. So you can visualize the field lines coming out because of this charge. Since the field line crosses these flat surfaces, there will be some flux linked with the flat surface. And as the field line also cross the curved surface, there will be some flux linked with the curved surface. They have said that the flux linked with the curved surface is phi. They are asking us what is the flux linked with the flat surface. So we will say the net flux coming out from this whole Gaussian surface has to be charge inside upon epsilon naught. And let's say the flux coming out from this one of the flat surface is phi dash. Because of symmetry, the flux coming out of both the flat surfaces will be same. So if the flux coming out of this right flat surface is phi dash, then the flux coming out of this left flat surface will also be phi dash. So we will say due to symmetry, say the flux linked with the flat surfaces is same, and let's call it phi dash. We can say that the net flux coming out equals to Q in by epsilon naught. The flux linked with the curved surface is phi. I have assumed that the flux linked with the flat surface is phi dash. So phi dash because of this one, phi dash because of this one, and phi because of the curved surface. So the net flux coming out will be due to curve plus due to flat. That will be phi plus phi dash plus phi dash. So phi plus 2 phi dash. The net flux coming out equals to Q in by epsilon naught, and the net charge inside this particular cylinder is just Q. So we can find from here phi dash. Simply move the phi to the right hand side. So you get phi dash equals to Q by epsilon naught minus phi divided by 2. And then you can open up this bracket and write phi dash equals to Q by 2 epsilon naught minus phi by 2. This is how easy the questions are based on Gauss law. Gauss law tells us that the net flux coming out equals to Q in by epsilon naught. That's all. So let's see the next example. Question goes like, imagine a spherical Gaussian surface to be made up of two hemispheres S1 and S2. So this whole three-dimensionally closed Gaussian surface, a sphere, is made up of two halves. The upper hemisphere is S1 and the lower hemisphere is S2. A charge Q is placed inside it. Where? Will tell. Determine the flux linked is higher with which surface in each case. When you place the charge at A and when you place the charge at B. So first visualize the charge to be placed at A and forget B. So if you have got a spherical surface and you have placed a charge Q here off center. Now with which half more flux will be linked? So flux represents what? The number of field lines crossing. So rather than thinking of the electric field strength and the surface area, I recommend it to students to visualize the electric field lines coming out of the charge. If let's say some electric field lines are coming out of this charge, for the sake of understanding I am drawing it symmetrically. Okay. The number of field lines crossing the upper half is same as the number of field lines crossing the lower half. So if you place the charge at A, then the number of field lines crossing the upper half will be same as the number of field lines crossing the lower half. Hence, the flux linked with S1 will be same as the flux linked with S2. So if the charge is placed at A, then the flux linked with S1 equals to flux linked with S2. How much? You will say, sir, if you place a charge Q, then the net flux coming out will be Q by epsilon naught. So the flux linked with upper half will be Q by 2 epsilon naught and the flux linked with lower half will be Q by 2 epsilon naught. But what if we place the charge at B? So visualize the same sphere, it's an imaginary Gaussian surface, and place the charge at B. Now, if you visualize many field lines coming out of it, so this way, okay. But think of it symmetrically, right? You can see that the number of field lines crossing the upper half, 1, 2, 3, 4, 5, 6, 7, 8, are more than the number of field lines crossing the lower half. Since the number of field lines crossing the upper half will be more, that's why the flux linked with the upper half will be more than the flux linked with lower half. So if the charge is placed at B, since more number of field lines will cross through the upper surface, that's why the flux linked with the upper surface will be more than the flux linked with the lower surface. But still, you will say that the flux linked with upper surface plus the flux linked with lower surface has to be equals to the total charge enclosed upon epsilon naught. So the net flux still combined with the both surface will be Q by epsilon naught, but the flux linked with the upper half will be more than the flux linked with the lower half. Let's see the next example. So question is, there is a point charge Q placed symmetrically at the center of a cube. Question is, if the charge Q is placed at the center of a cube, determine the flux linked with each face of the cube. So you know that because of this charge, field lines will be coming out in all the three dimensions. Due to symmetry, flux linked with each face will be same. So if the flux linked with this face is phi, then the flux linked with this face is also phi, and the flux linked with this face is also phi. And a cube has got 6 faces, 1, 2, 3, 4, 5, 6. So you will say the flux linked with each face is, let's say, phi. So you will say the net flux coming out, which will be 6 phi through the 6 face, has to be equal to the total charge inside upon epsilon naught. Hence, the flux linked with one of the phase has to be q by 6 epsilon naught. They will never ask you this question in this way. They will ask you the same question but in a different way. They will say that we have a square plate of side length A, and at a distance a by 2 above its center we have placed a charge q. Determine the flux linked with this plate. So you will say that, sir, this is the same case as the q. It's just that rather than looking at the all 6 faces, you are looking at only one of the face. So if I think of one square of side length A and I place a charge q at a distance a by 2 above its center, then the flux linked with this particular face has to be same as the flux linked with the lower face of this cube. And we know that the flux linked with the lower face of this cube, one of the face is q by 6 epsilon naught. So if you have a charge q placed at a distance a by 2 above the center of a square of side length A, then the flux linked with this square plate has to be nothing but q by 6 epsilon naught. So the flux linked with the square plate is nothing but q by 6 epsilon naught. It is just that you are looking only at one of the face out of the 6 faces of a cube. Okay. Now I will talk specifically about the cube cases. So let's talk about the cube cases. So if you have placed a charge at the center of the cube, then the flux linked with each face of the cube is nothing but q by 6 epsilon naught. We have just done this. But what if the charge is placed on one of the edge of the cube, let's say here. Now here I am trying to explain one important concept. This charge will produce field line, yes. Think of the two faces containing this charge, this face and this lower face. These two faces are the one containing this charge. Now listen to the statement carefully. The plane which contains the charge, through that plane the flux linked is 0. What? The plane that contains the charge, through that plane the flux linked is 0. Why? Think that you have a plane, yes, and on the same plane you have placed a charge. The charge will produce electric field at every place on the plane, yes. But if you think of one small area, let's say dA, the direction of area vector will be perpendicular to the plane, and the field due to this charge for this small area will be along the plane. So the field will be along the plane and the infinitely small area vector will be perpendicular to plane. Since the infinitely small area vector is perpendicular to plane and field is along the plane, they are perpendicular. So the dot product comes out to be 0. So if a plane contains a charge, the flux through that plane is 0. So here for these 6 faces, the two faces on whose common edge we have the charge q, the flux linked with these two faces is going to be 0. Okay. So flux linked with the two faces containing the charge is 0. This is something important you should know. So the flux linked with this face will be 0 and the flux linked with this face will be 0. Now there are 4 faces left. What will be the flux linked with these remaining 4 faces? So you will say one can think of this charge q to be enclosed in 4 identical cubes. So visualize this charge q to be trapped in 4 identical cubes. You have done something like this in your study of solid state. So one edge is shared among 4 identical unit cells. So all the flux coming out of this charge q will go equally through these 4 identical cubes enclosing it. The net flux coming out of these 4 identical cubes will be the charge enclosed by these 4 identical cubes upon epsilon naught. So the flux coming out of one of the cube has to be equals to q by 4 epsilon naught. So the charge q is shared symmetrically in 4 cubes. So the flux linked with one whole cube with the 6 faces of this single cube will be nothing but q by 4 epsilon naught. And out of these 6 faces, remember that there will be no flux linked with the 2 faces containing the charge. Similarly, if they give you the case that the charge is placed at one of the corner of the cube, you have done the course on solid state. If yes, good. If not, good. Remember that In a unit cell, the atom is shared among the 8 unit cells. So a corner will be shared among 8 identical cubes. Now here there are 3 faces which contain this charge: face 1, face 2 and the top face 3. So a corner is shared between 3 faces: the top face 1, the back face 2 and this side face 3. Okay. So the flux linked with the 3 faces containing the charge is 0. So there is no flux linked with the 3 faces containing the charges. There are 6 faces. 3 faces contain the charge: face 1, face backward, face side. So the flux linked with the 3 faces containing the charge is 0. The flux linked with the other 3 is q by 8 epsilon naught. Sir, how do you know q by 8 epsilon naught? Because to completely enclose this charge, I will have to place 8 identical unit cells. So the net flux coming out of one of the unit cell will be equals to q by 8 epsilon naught. Hence, out of this q by 8 epsilon naught, through 3 phases, the flux is 0. So through the remaining 3 phases, the flux is 8 q by 8 epsilon naught. So you can say, as 8 identical cubes will be required to enclose this charge, the flux linked with one of the cube will be q by 8 epsilon naught. Flux through one of the other 3 phases, through which the flux is not 0, will be q by 24 epsilon naught. Here, out of the 6 phases, through 3 phases, the flux is 0. Yes. For the other 3 phases, let's say the flux is phi dash. So you will say that the net flux coming out of this cube will be phi dash plus phi dash plus phi dash, and that equals to q by 8 epsilon naught. So the flux linked with one of the remaining 3 phases will be equals to q by 24 epsilon naught, as 3 phi dash will be equals to q by 8 epsilon naught. This is simple thing that you should be able to understand. Let's move on. So a question comes here. If an electric field E equals to alpha x square I cap exists in space, determine the charge enclosed in a cubical surface of side length A shown in the figure. So here we know that an electric field equals to alpha x square exists in the x direction. Alpha x square exists in the x direction. You need to determine how much charge is enclosed by this cube. How much charge is enclosed within this cube. So how to find? We know that the net flux coming out of this cube has to be equals to the total charge inside upon epsilon naught. Yes, sir. Now what will be the net flux coming out of this cube? Now see, this cube has got 6 faces, right? The electric field is in x direction. We get the flux due to the field line that crosses. So out of these 6 faces, the flux will be linked only with 2 faces: the frontmost face and the backmost face. Only with these 2 faces, electrical flux will be linked, right? So you will say the electrical flux is linked only with these 2 faces. At the first phase, the backmost phase, what will be the electric field strength here? So we know that at any x coordinate x, the electric field strength is alpha x square. For this leftmost phase, the flux will be equal to the electric field strength here multiplied by its area. The area will be a square. What is the strength of the electric field crossing? So you will say, sir, for this particular phase now, the x coordinate is 0. Since for this particular phase the x coordinate is 0, the electric field strength at this particular phase will be 0. So electric field strength is 0 and the area is a square. So the flux linked with the leftmost phase will be 0. Why? Because at x equals to 0, the electric field strength is 0. Now there will be some flux linked with this phase as well. Now you will say, for this frontmost phase, the x coordinate is nothing but a. If the x coordinate is a for this phase, the frontmost phase, what will be the strength of electric field here? So the strength of electric field here will be alpha x square. Here x is a, so you get alpha a square. So the electric field strength at the place of frontmost phase is alpha a square and the area of this phase is a square. So the flux through this particular phase, the frontmost phase, will be alpha a square into a square, that becomes alpha a raised to the power of 4. So there are in totality 6 phases. Since the electric field is in x direction, we will say the flux linked with the 4 phases perpendicular to the direction of field will be 0. So there will be flux linked only because of these 2 phases, the backmost and the frontmost. Out of these, for the backmost phase also the flux will be 0 because at its position the x coordinate is 0, so the electric field is 0. And for the frontmost phase, the x coordinate is a, so the electric field strength is alpha a square. So as the electric field is in x direction, flux will be linked only with the surfaces which electric field crosses. That is the faces parallel to the yz plane. The faces parallel to the yz plane. This face at x equals to 0 and this face at x equals to a. At x equals to 0, the electric field strength is alpha into 0 square, which is 0. So the flux linked with this particular phase will be 0. At x equals to a, for the frontmost phase, you will say that the electric field strength is alpha into a square. So that will give you alpha a square. So the net flux coming out of the cube will be equals to, here there is no field, hence there is no flux. Here you have got a field of alpha a square and the area is a square. So the net flux coming out is alpha a square into a square, that becomes alpha a raised to the power of 4. The net flux coming out equals to q in by epsilon naught. So you can say alpha a raised to the power of 4 equals to q in by epsilon naught. Hence you can say the charge enclosed within this cube has to be equals to alpha a raised to the power of 4 into epsilon naught. So these type of questions are a standard question. When a child looks at this particular question, they get perplexed that what to do with this particular problem. If you start visualizing what the examiner is saying, the electric field exists in x direction, its value keeps on changing as the x changes, and you apply Gauss law, you will get the answer. This is an easy question which looks tough. It looks tough, but it's an easy question. So let's move on to how to use Gauss law to determine the field strength due to different system. So first, let's say we have got an infinitely long line charge of charge per unit length lambda. So if we have got this infinitely long line charge of charge per unit length lambda, how can we use Gauss law to determine the electric field strength due to it? So visualize a cylinder around the line charge. At a point on this cylinder of radius r and length l, let's say the electric field strength is E. Now, if you have visualized this closed Gaussian surface in the form of cylinder, there will be some flux linked with the curved surface and there will be some flux linked with the flat surface. Here kids understand that there will be no flux linked with the flat surface. Why? The electric field produced by the line charge will be here, and for this top flat surface the area vector will be in the direction upwards. So the angle between electric field and area vector is 90. So there will be no flux linked with the two flat surfaces. So the flux linked with the flat surfaces will be 0. Only the flux will be linked with the curved surface. If you think of one infinitely small area here, dA, you will say since the electric field and area vector are parallel, the infinitely small flux will be equals to E into dA. So the net flux on integration comes out to be E into the overall curved surface area, and the overall curved surface area will be nothing but 2 pi r into L. So the net flux coming out from the curved surface will be equals to E into 2 pi r L, and the net flux coming out has to be equals to Q in by epsilon naught. Within this Gaussian surface, how much charge is enclosed? So the charge equals to on a length L. On this length L, how much charge will be enclosed? So if the charge per unit length is lambda and the length is L, then the charge enclosed will be lambda L. So you will say the net flux coming out E into 2 pi r L equals to the charge enclosed within the Gaussian surface, which is lambda L upon epsilon naught. Cancel out L and L both the side. So you get E to be equals to lambda by 2 pi r epsilon naught, multiply 2 in both numerator and denominator. So you get 2 lambda upon 4 pi epsilon naught r. Why have I multiplied this 2 in numerator and denominator? So that this 4 pi epsilon naught can be written as K. And you get the electric field strength to be 2K lambda by r. We have already learned this formula when we were talking about the field strength due to a line charge at distance r. but now you know from where does it come and how it can be derived using the Gauss law. So now let's talk about field due to a shell. So if you have a shell of charge q and radius r, for r less than r, an inside point, since the shell has a spherical symmetry, think of a Gaussian surface inside the shell whose distance from the center is r, for distance from the center less than the radius. This is a three-dimensional Gaussian surface. Now let's say because of the three-dimensional symmetry, at a point on this Gaussian surface we get the electric field to be E. Now if we try to write the flux linked with this particular Gaussian surface, we will say that if I take an infinitely small area dA, the area vector and field vector are parallel, so the d phi will be simply equals to E into dA, and when I integrate it, on integration of dA, the magnitude of the infinitely small area, I get the overall surface area, so I get E into 4 pi r square. The net flux coming out equals to Q in by epsilon naught. But what is the charge enclosed within this Gaussian surface? Zero. Why? Sir, it's a shell. The charge is on its surface. Within this Gaussian surface, there is no charge. So E into 4 pi r square equals to 0 because there is no charge inside. That's why we say the electric field inside the shell because of the shell is 0. Now for an outside point, if you think of a Gaussian surface of radius more than the radius of the shell, again because of the three-dimensional symmetry at a point, let's say the electric field is radially outward. Again, if you think of an infinitely small area, the angle between E and dA will be 0, and on integrating you will say that the net flux coming out of this whole closed Gaussian surface of radius r will be equals to E into 4 pi r square. So for outside point, E into 4 pi r square, the net flux coming out equals to Q in by epsilon naught. Now the total charge inside this bigger Gaussian surface equals to the charge on the shell. So Q by epsilon naught. So you can bring this 4 pi r square down here. So what you get is E equals to Q upon 4 pi epsilon naught r square, and you can write this 4 pi epsilon naught as K. So you get equals to KQ by r square. That's why the field inside the shell because of shell is 0, and for outside point you can assume the entire charge to be at center. So now we will find the field due to a solid non-conducting uniformly charged sphere. We have already done the formula what is the field strength for r less than r and for r greater than r. What we are trying to do here is we are trying to understand how can we find it using the Gauss law. So for a distance r less than the radius, if you are at some distance from the center which is r is less than the radius, how to determine the electric field at such a distance r? So think of a Gaussian sphere of radius small r. Because of the spherical symmetry, at each point on this Gaussian sphere, the electric field will be radially outward. Now think of one of the electric field and one infinitely small area here dA. Since the electric field and area vector which is normal to the surface area will be parallel, you will say d phi equals to electric field into the infinitely small area into cos of the angle between them which is 0, and cos 0 becomes 1. So you get E into dA. Now what is this dA? The magnitude of infinitely small area. When you integrate the magnitude of infinitely small area for the whole sphere, what you get? The surface area of whole sphere. So on integrating you will say that the net flux coming out of this Gaussian surface has to be equals to E into the surface area of this Gaussian sphere which is 4 pi r square. So you can say that the net flux coming out E into 4 pi r square has to be equals to the charge enclosed within this Gaussian sphere upon epsilon naught. Now what is the charge enclosed within this Gaussian sphere? Sphere, 3 dimension. So you will say, sir, in the whole sphere of radius capital R, the charge enclosed is Q. So within this Gaussian sphere of radius small r, what will be the charge enclosed? How to find? Better use the charge density. If the whole sphere of radius capital R has a charge Q and the charge is uniformly distributed, you will say that the charge density will be the total charge upon total volume, 4 by 3 pi r cube. And the volume of this Gaussian sphere is 4 by 3 pi into small r cube. So the charge inside the Gaussian sphere has to be equals to charge density multiplied by the volume of the Gaussian sphere. and the volume of the Gaussian sphere is 4 by 3 pi r cube. So the charge inside the Gaussian sphere has to be total charge upon total volume. That gives you the charge density multiplied by the volume of the Gaussian sphere. So you will say the net flux coming out of this Gaussian surface equals to total charge enclosed upon epsilon naught, and the total charge enclosed is total charge upon total volume multiplied by the volume of Gaussian sphere. Now here you can cancel out 4 by 3 pi, 4 by 3 pi. So on the right hand side you get q into r cube upon r cube divided by epsilon naught. So since you can see E into 4 pi r square equals to total charge into radius of Gaussian sphere whole cube upon radius of the sphere whole cube divided by epsilon naught. Bring this term down here and you will get, on cancelling r square with r cube, here you get an r. What you get is E equals to qr upon 4 pi epsilon naught r cube. In place of 1 by 4 pi epsilon naught, you can write k in the numerator, and I personally like to write it as kq upon r square. This becomes k, there is a q. In place of r cube in denominator, write r square into r, and in numerator there is an r. Writing it this way tells you that as you go from center to surface, the electric field strength increases linearly. Now for outside point it is easy. You can simply think of one infinitely small area due to symmetry, electric field E. So the net flux coming out for r greater than r equals to E into 4 pi r square, and the charge enclosed by this bigger Gaussian sphere is the entire charge on this sphere. So this has to be equals to q by epsilon naught. So what you get is E equals to kq by r square. We have already done these formulas. I'm just telling you from where did they came. One formula which I haven't explained is the field due to infinitely large plane sheet, and this is important. So think that you have got an infinitely large plane sheet. Okay. So from the side you will just see a line. Now if it is positively charged, we know that the field will be coming out of it in both the directions. Yes, sir. Now what is the strength of field due to an infinitely large plane sheet of charge per unit area sigma at some distance from it? So we know that the formula comes out to be E equals to sigma by 2 epsilon naught, but from where does it come? So it can be proved using Gauss law. So let's say we have assumed a Gaussian pillbox. In NCERT the word used is Gaussian pillbox. But rather than thinking of pillbox, think that you have a Gaussian cylinder such that half the cylinder is on this side of plane and half the cylinder is symmetrically on the other side. Now on this cylinder there are three surfaces to be considered: the front flat surface, the back flat surface, and the curved surface. Since the electric field lines will be along the curved surface, so you will say that the flux linked with the curved surface of this Gaussian pillbox of the Gaussian cylinder will be 0. So the flux will be coming out only due to the flat surface on this side as well as on the other side. So if this sheet has got charge per unit area sigma, how to determine the electric field strength? So you will say flux linked with the curved part of this cylinder will be 0, as the electric field line doesn't cross it. Now the flux linked with the two flat parts will be same. If the electric field strength is E and I have taken the cross-sectional area of this cylinder to be A, then with each flat part on each side the flux coming out will be equals to E into A and E into A. So the net flux coming out because of the two flat part will be EA plus EA, that becomes 2EA. Now this net flux coming out equals to Q in by epsilon naught. What is the charge enclosed within this cylinder? So sir, on the plane now, think of this area A. This area of cross section of cylinder is A. So the charge enclosed in this much part will be sigma into A. So the net flux coming out 2EA equals to sigma A upon epsilon naught. So 2EA equals to sigma A upon epsilon naught. Cancelling out AA, you get electric field strength equals to sigma by 2 epsilon naught. So that's why remember that if you have got an infinitely large plane sheet with the charge per unit area sigma, if it is positively charged, the electric field is away from it equals to sigma by 2 epsilon naught, sigma by 2 epsilon naught. So now we are going to take some theoretical concepts here. Understand that day in, day out, NEET is becoming more and more theoretical. So these theoretical points are important. So you have to tell me each statement here is true or false. So starting with the first statement. If the net flux coming out of a Gaussian surface is zero, the electric field at each point on the Gaussian surface is zero, yes or no? If the net flux coming out of a Gaussian surface is zero, then the electric field at each point on the Gaussian surface is zero. We know that the Gauss law can be written as the net flux coming out equals to Q in by epsilon naught, yes. Or we can even write it as closed integral of E dot ds equals to Q in by epsilon naught, yes. So if they are saying if the net flux coming out is zero, then the electric field at each point on the Gaussian surface should be zero. Yes or no? Answer is no. Think that you have a Gaussian surface in which you have got two charge plus Q and minus Q. If you have got two charge plus Q and minus Q, there will be not even a single point on this Gaussian surface where the electric field strength will be zero. But since the net charge inside the Gaussian surface is zero, the flux linked with this whole Gaussian surface will be zero. If you have got charge plus Q and minus Q, then the number of electric field lines exiting will be same as the number of electric field lines entering. That's why the net flux linked will be zero, but at no point on this whole surface you will find zero electric field strength. So this is important. So this statement is right or wrong? It is wrong. Next. If the electric field at all points on the Gaussian surface is zero, flux linked with the surface is zero. If you have a Gaussian surface, and if at each point on this Gaussian surface the electric field strength is zero, is the flux linked with this Gaussian surface zero? Yes. The net flux coming out of a Gaussian surface can be written as closed integral of E dot ds. If at each and every goddammit point the electric field strength will be zero, then you will say that the net flux coming out has to be zero. Yes. So if at each and every point on the Gaussian surface the field strength is zero, then you will say that the net flux coming out of the surface is zero. Yes, this statement is true. Moving to next one. Gauss law can be used to determine strength of electric field in all cases. I have just used the Gauss law to determine the strength of electric field for a line charge, for a shell, for a non-conducting sphere, for a sheet. So question is, we can use Gauss law to determine the strength of electric field in all cases, yes or no? No. We can use Gauss law to determine the strength of electric field only in case of symmetrical cases. When you can think of a Gaussian surface on which at each point the strength of electric field will be same, then only you can use the Gauss law to determine the strength of electric field. So can you use the Gauss law to determine the strength of electric field in all cases? No. If let's say somebody give me three charges minus 2 coulomb, 4 coulomb and 6 coulomb and ask, tell me what is the strength of electric field here. So I can't visualize a Gaussian surface using symmetry through which I will be able to find the electric field strength here. That's why you can't use Gauss law to determine the strength of electric field in each case. So where can we use Gauss law to determine the strength of electric field? Only when you have got symmetric cases. So you can think of a Gaussian surface. So Gauss law can be used to determine the strength of electric field in all cases. Answer is no. Next question. Gauss law works only on symmetric charge distribution. Yes or no? Gauss law works only on symmetric charge distribution. Yes or no? Beta, Gauss law can be utilized to determine the electric field for symmetric charge distribution. That's a fact, yes. But Gauss law can be applied only on symmetric charge distribution. This is wrong. Even if you have got charge of minus 2 coulomb and 4 coulomb and you think of any Gaussian surface enclosing them, I can say from Gauss law that the net flux coming out of this closed surface equals to the total charge inside 2 coulomb upon epsilon naught. So the net flux coming out equals to Q in by epsilon naught can be used when? In all cases. But the Gauss law can be utilized to find the electric field only in case of symmetric charge distributions. So question is, Gauss law works only on symmetric charge distributions. Yes or no? So Gauss law even works when you have got asymmetric charge distribution. So this statement is false. So these are some theoretical questions, and with this I conclude the Gauss law. Now this video has been long enough already. We'll post dipole in the next video. See you guys in the next hour. Bye bye. So that's all for now. See you guys in the next hour.